Okay, welcome everybody. Before we start, we're going to have a little German lesson. I before E is pronounced Rieker. E before I, like Steinbrenner, is pronounced like an I. Anyway, we are pleased to have Greg Rieker from Mechanical Engineering at CU. Greg is originally from Lakewood, Colorado, and did his undergraduate at University of Missouri-Rolla, and then went on to Stanford to do his graduate work in mechanical engineering. And then he worked for a few years as at a startup company out in California, and then did a postdoc here in Boulder at NIST, where he started doing more of the laser comb spectroscopy, and then joined the mechanical engineering department at CU 4 years ago. So I'm welcome to have Greg here, and you can take it away.
Excellent. All right. Is this too loud, or is this okay?
Okay, great.
Good. All right. Great. So thanks, and thanks, John, for the invite. It's very exciting for me as a mechanical engineer that's trying to take basic physics tools out of the physics laboratories and convert them into usable instruments, to get the chance to talk with researchers that are actually out in the field and doing some of the work that could use these kinds of tools. And so I'm hopeful that in some of the things that I'll show you today, you might see something that would play into your own research. And feel free to contact me afterwards, because we're looking for a lot of places we can start to take these instruments. So I'm going to talk, the title here, I'm going to talk about frequency comb spectroscopy of atmospheric trace gases. And the frequency comb, as the title implies, is sort of a unique laser tool. So most lasers emit a single wavelength of light. It might be tunable over a short range. Frequency combs, which are a Nobel Prize technology that came out of the physics department here at CU, emit hundreds of thousands of wavelengths, very distinct, sharp, narrow wavelengths of light, all at the same time. And so, as I'll hopefully show you through this talk, there's a lot of unique capabilities that this laser might open up for us in the future. I wanted to recognize my group. This is the Precision Laser Diagnostics Lab at University of Colorado. We're mechanical engineers, and we wake up every day to create sensors to make measurements that aren't possible yet in energy, and what I mean by that is industrial and combustion systems, and in atmospheric systems, which is what I'll focus on today. I want to especially recognize these folks in my group, research associates Sean Coburn and Carolyn Alden, who are big into the methane leak detection work I'll talk about, and Nazanin Hoghugi, who's into this compact sensor that I want to talk about at the very end as something new that we're working on. And then Robbie Wright is our engineer. This guy is amazing, built a lot of the instruments you'll see today. None of this would be possible without Nate Newberry and Ian Connington. Those are the people that I postdoced with at NIST and continue to work with on these projects. And Colm Sweeney and Peter Tanz and others have been really kind of keeping our feet on the floor in terms of what we need to do for oil and gas and other atmospheric sensing to make these tools make sense. Okay, trace gas sensing is what this talk is about. It can mean a lot of things. We do work in atmospheric monitoring, so really looking downstream of the stack, so looking at emissions detection, methane leak detection that I'll talk about today. We also do work upstream of the stack, so working in combustion environments to take the same tools to understand chemical kinetics and adjust those processes to sort of mitigate. So we're both trying to detect and through detection help mitigate, but also try to change the combustion processes to improve what's coming out of the stack. So trying to fight both sides of the battle there. But in general, I want to start this talk out by talking about trace gas sensing, what's important and what is ideal, and then I'll talk about our instrumentation along in this context. So when it comes to trace gas sensing, one of the most important things for many measurements is stability and low drift. So you want to be able to take measurements over time and between instruments and make comparisons. And if we take a measurement on day 1 and we take a measurement on day 5 and we see a change, we want that change to be due to the system we're measuring, not the instrument itself. So that's important. Precision and sensitivity, which are related but different. We want to be able to detect small changes. For the methane that I'll talk to you about, the methane background is moving all over the place, and we're looking for tiny enhancements when we're looking for new leak sources. And then, of course, trying to detect small concentrations is important also. And then for accuracy, it's nice to be insensitive to interference from other molecules, from water vapor that's coming in and out of the atmosphere very rapidly and can cause, for example, your methane concentrations to change without a new source or sink being added to the system. And in some cases, we want to be able to link to like World Monitoring Organization scales so that we're calibrated with them. That's what's really important. This is sort of what's ideal for different measurements. Continuous, you might be able to want to make measurements at night, during the day, different cloud cover. So we're pushing towards that. High-speed monitoring for combustion. When we're talking about big, long, open path measurements, like what I'll show you today, we can't calibrate this instrument because we can't, pull a vacuum on the Earth and put in a purge gas. So we need to be able to not have to calibrate that instrument. Multiple species is nice. And then finally, portability and low cost. If I want to build an instrument that I can give to a scientist to go out in the field without me being there, this really needs to be portable, low cost, robust. So we're thinking about that as we go. So one possible approach, the approach that we take, broadband, ultra-high resolution absorption spectroscopy using frequency comb lasers. And if I do a good job in this talk, you'll understand what I mean by that statement by the end. Okay, so here's an overview of the talk. I'll spend some time talking about dual frequency comb spectroscopy. And I do that because I think it hopefully shows some of the uniqueness of this instrument and some of the benefits that we can then leverage into these areas such as methane leak detection and then compact multi-species detection. Are there very many people here that use Picaro instruments or are familiar with them? Okay, so I'll talk about, this is related to that, kind of taking our modalities and moving them towards that Picaro platform. Okay, one slide on laser absorption spectroscopy because this is sort of what everything is built on. The idea is to take a laser, shine it through a gas sample. It could be a combustor, it could be 2 kilometers of open atmosphere to a detector, and then we quantify the transmission of the laser light as a function of wavelength. So this is a simulation of the transmission over a 2-kilometer path in the atmosphere. It's the near infrared here. So you can see all these dips in the laser transmission, and that's due to absorption by different species in the atmosphere, water, CO2, et cetera. And if you zoom in, these dips are composed of hundreds of individual rotational vibrational features. That's where the light is absorbed by rotation vibrational transitions in the molecules. And the depth and the shape of those individual features is a function of temperature and pressure and the concentration of the species that you're measuring. And so if we probe the depth and the width, we can back out the concentration and other things that we care about, like temperature. So looking at this, you can see there's a lot of dips here. Each one is sort of unique to the different gases that are producing that absorption, and they span across several hundred nanometers. So I think you can start to get an idea of why I would want a laser source that has hundreds of thousands of wavelengths. So I've got a slide here on the frequency comb. It's a coherent, stabilized femtosecond mode-locked laser. That's a mouthful. But at the end of the day, what this means is we take a laser, we create some kind of a cavity, so in this case, a ring of optical fiber that allows a pulse to move around in that ring. We put a broadband gain medium, in this case, erbium-doped fiber, that'll let this laser laze at many different wavelengths. We have some kind of a mode locking mechanism, which is there to force the laser into very short pulsed operation. And so when you do that, if you peel off just a small part of each pulse as it goes around, so maybe 100 femtosecond pulse, and if you do the Fourier transform of that in the frequency domain, what we end up with is hundreds of thousands of individual, unique wavelengths of light that are perfectly spaced by the pulse repetition rate of that laser. And what makes this special, what makes it a frequency comb instead of a mode-locked laser, is we take very special care to control the exact length, everything about this cavity so that every pulse is identical. And when you do that, then those frequency elements are stable at known wavelengths, known spacing, just to extremely high precision. If none of that made any sense, the bottom line is the output of our laser looks a lot like 100,000 very well-behaved lasers. So that's where the title comes from. Okay, so now we want to do spectroscopy with this source. We've got 100,000 different wavelengths of light. We want to shine them through a gas that will impart some absorption at certain wavelengths. The question is, how do you actually quantify the absorption on each of these individual wavelengths? There's a lot of information in there. So our colleague Ian Coddington at NIST about 10 years ago pioneered a really interesting way to do this called dual frequency comb spectroscopy, where we make things even more complicated by getting a second frequency comb, interfering it with the first frequency comb, on a single photodetector. So I'll show you a picture later. It's the size of my hand. And as I'll describe in a moment, we can do tooth-by-tooth readout of the absorption. I like to explain this because again, I think this is one of the neater aspects of the physics of this project. It's based on something called heterodyne detection. So if you have two wavelengths of light, they might be in the hundreds of terahertz in the near infrared. That is much faster than the bandwidth of our detector. So the detector can't tell the difference between those two wavelengths of light. But when these two wavelengths of light strike the detector, if the spacing between the wavelengths of light is down in the, say, megahertz regime, in the RF regime, that's where our detectors have enough bandwidth. So what we get when we strike two of those frequencies onto a detector is a beat note that is at the difference frequency between the two. So if we have 50 megahertz spacing, we get a 50 megahertz beat note on our detector. In dual frequency comb spectroscopy, we do this on a grand scale. So we'll take our two frequency combs and we'll lock them up so that the two wavelengths of two of the comb teeth line up exactly. And then, as I mentioned, the pulse repetition rate sets the spacing of these teeth. So we'll take one of the laser cavities, stretch it a tiny bit, a few microns maybe. That changes the time that the pulse goes around, slows down the repetition rate, and it narrows up the spacing between the comb teeth. So then as you move across here, each individual pair of comb teeth has a different offset, and that gives rise to a different unique beat signal in our detector. If we add in an absorbing gas, some of those teeth are absorbed and weakened, and we see a weakening in the RF beat signals that our detector sees. So if you've ever played an instrument, and you want to tune it, somebody plays a reference tone, you play another tone, and you can hear a little wavering, and then you try to tune yourself till that wavering goes away. That's heterodyne detection that you're doing, and that's what we do here. So it's really like a symphony of optical frequencies that are all out of tune with each other. The poor detector must sound terrible. So then we can recover back this optical frequency, or the absorption spectrum. So I want to show, that's the kind of the cartoon method. I want to show some of the real data here from a system. So I'm zoomed way in on a single one of these beat notes here. The comb tooth line width is about 10 to the minus 11 nanometers, and the accuracy of the wavelength is about 10 to the minus 8. So almost perfect in terms of a sharp wavelength element where we know the optical frequency. So then we can relate back that RF frequency that we see on the detector to the optical frequency of the comb teeth that contributed to it. And what I'm going to do is start zooming out. So this is zoomed out a factor of 5. This is a factor of 50 zoomed out. Now you can start to see the neighboring comb teeth coming in. The separation between these comb teeth is about 100 megahertz. So that's 0.8 picometers, very close together. Zoom out again, this is a factor of 500, and now you can start to see some water vapor absorption. So I have an absorption cell in the path of my laser beam. So that's a single water vapor absorption feature. If I zoom out a factor of 2500, now the resolution of this detector, or this projector, is not good enough to see the density of these modes. So I'm just going to connect them with a line now. But you can see about 5 water vapor features. This is the fast scan range of a DFB diode laser. That's the workhorse of open path sensing for many years, tunable diode laser. Now I'm going to zoom out. This is a factor of 25,000. Lots and lots of water vapor absorption. Here's 100,000. You're starting to see some of the natural intensity spectrum, the curve of the actual output of the combs. Lots and lots of features there. Now there's 200,000 and 500,000. So this is 131,000 comb teeth that are just perfectly resolved across a spectrum, in this case of about 2,100 water vapor absorption lines. So it's like we can see the forest and the trees. We see a very broad wavelength span, and we see every little wavelength along the way. And one of the neat things about this system is it takes about 2.5 milliseconds to get this spectrum. To get that signal to noise ratio, we need to average many, so sort of seconds to maybe minutes if you want to, just depending on how you configure your system. But nevertheless, it's very fast compared to something like a Fourier transform infrared spectrometer, which is the nearest analog to this. Okay, so where it all started was up at NIST, as I mentioned, or as John mentioned with my postdoc. This technique had been around for a few years at that point, but had just been used for some simple laboratory spectroscopy. We didn't know that it would work over a turbulent atmosphere. Myself and Ian and Nate came up with some interesting experiments to launch the light of the comb up over a kilometer to the top of Kolar Mesa, and this is what John mentioned in his email. If you go walk along the top there, there's some trails. You can see the retroreflectors that we're using. It's all eye safe, but if you stand in front of the mirror, you will in fact disrupt our experiment. There's many times I'd lose signal and I'd be checking the system and I'd look through the scope and somebody would be looking at our mirror, you know, and it is what it is. So this was a nice test bed to start things up because we had a tower in the middle that we could put a Picaro analyzer that was calibrated to measure methane, water all at the same time. I'll show that later. So this is some of the very first spectra that we got off of this big, long, open path in the atmosphere. What you're looking at, this is absorbance versus wavelength, and that's just the amount of laser light that's absorbed at each wavelength. And you can see methane absorption features, CO2 absorption features, water is this small stuff down there, HDO, 13 CO2. It all comes through in the spectrum of about 50,000 comb teeth in this case. And so what we can do with that is fit this with absorption models. So we have a pretty good idea of what the absorption for methane and water should look like at atmospheric conditions. So we'll build a model for each of the species. We fit all of those models to this absorption spectrum all at the same time, and from that we can extract the concentration. So this is nice because we get multiple species concentrations, but it's also nice because it accounts for all the tiny little bits of overlap between the different species. So that's one of the things that broadband really helps you with is dealing with, you know, the interference between all of these species. We fit them all at the same time. At the end of the day, the wavelength on this thing just doesn't drift compared to the width of these lines. And also, we have so many spectral elements in there, there's zero instrument line shape, so there's no distortion that you need to take care of. And those are two of the main things that can cause drift in absorption spectrometers. So this thing has incredibly low measurement drift, speciation, as I mentioned before, and since we're measuring water vapor, we can deal with doing dry air corrections, you know, for the methane concentration. So a lot of really nice things that come out of this spectrum. Then this is one of the neater parts. The absorption model itself serves as the calibration. So as I mentioned, these spectrometers are very, very precise. NIST built a spectrometer, we built a spectrometer, and we actually sent them over the identical same path, had two different postdocs running the machines, and the spectra agreed to about a part in 1,000 across the whole thing. So there's very little instrument-specific distortion. So if we use the same absorption model on both of those spectra that are measured to back out our concentrations, we get the same number down to this part in 1,000 level, about 0.1%. And so these absorption models serve as the calibration, and once you have a good model, then all of your instruments can just share that model. And if we have high accuracy in the model, we'll have high accuracy in the measurements. We can also take those kind of spectra, take 5-minute spectra, and then fit them at each 5-minute interval, and back out CO2, methane, water, HDO as a function of time. So you can see the different, diurnal cycles of methane and CO2 in the atmosphere above Boulder, changes in water, temperature. And then behind here, you can kind of see a little black line. That's the Picaro trace. And so we track it very, very well. There's some discrepancy, and some of that is because we're doing a 2-kilometer path, and the Picaro is measuring just the atmosphere right around where the Picaro is. So very nice things there. So to come back to the trace gas sensing, as I was mentioning earlier, what's important, stability, low drift. We have low or no wavelength drift in these systems, essentially. No instrument line shape, so there's very little in the instrument that can drift. The precision and sensitivity, because we have low drift, we can average as long as the atmosphere will let us average. And what I mean by that, as you'll see later in some Allen deviations, is we can average until basically the fluctuations in the atmosphere become bigger than the fluctuations in our instrument. And then accuracy, again, the absorption model is the calibration. So if you're accurate there, you can link back to WMO scales and other things. And then, obviously this will work day, night, whenever. Eventually in deep rain or heavy rain or snow, we'll lose our signal. Low, no calibration, multi-species. But then the portability, low cost problem. So when I did this experiment at NIST back in 2012, this was the proof of concept spectrometer. So It's about $500,000. There's a giant rack of analog electronics over here. We called it the spaghetti monster. There's an optical stabilized table back here, another stabilized table here. So the instrument was a bit of an overwhelming, a bit of a beast, really. And so at that time, I had no idea how we were going to make something practical happen out of this. But at that same time, Laura Sinclair and Ian Cunnington over at NIST were working on some very robust frequency comb designs. Designs that are based on optical fibers, so telecommunications optical fibers that are very robust themselves. They shrunk it down to about a foot by a foot box, and we're even smaller than that now. We put that in the back. That's actually my parents' conversion van. We put it in the back of my parents' van and drove it up a bumpy road and showed that we could keep the wavelength stabilized. And so that in about 2014, at the same time we were doing those outdoor experiments, this was coming together and starting to show a path to a practical device. With one click here, I'm going to fast forward 2 years because it took some time to get this next step down. But we reduced that original instrument down to this instrument. So this is now a 19-inch rack mount that's about 30 inches tall. We reduced the cost by about a factor of 10. We got rid of some of the cavity-stabilized lasers and different things that made it so that we couldn't move this out of the laboratory. So this has been a neat advancement that we're finally able to move this thing. And so we have about 3 copies of this now. That's the world's first portable dual frequency combs. So far, we're the only ones to have them, which is nice. Okay, so now I'm going to talk about what we've then gone on to do with these portable systems. And the 2 examples I'm going to give are methane leak detection and then compact multi-species detection. So to start with the methane leak detection, this has been an area of intense interest lately because the uptick in natural gas in the United States has been very large because of horizontal drilling and fracking. And a lot of studies coming out of NOAA and other places are showing that there's more leakage from these systems than we think there is. And in fact, some of the measurements that we're doing north of Boulder at Table Mountain, when the wind is blowing from the west, we have one measurement of methane, and when the wind shifts and comes from the east, we see 300 or 400 parts per billion increase in methane almost instantly. It's really fast. So there's a lot of leakage going on out there. And so, the government recognized this, and the problem with regulating something like methane leaks is there's not a low-cost way to measure it right now. You could go out with a Picaro, which costs about $100,000, or I guess they're coming down now, but there's just no good way to get out there and probe all of these there's about 1 million active wells in the United States. So they really wanted to push to come up with ways to detect and size methane leaks at a very low cost per site and low annual cost. So that sort of sets the stage. This is funded by the Department of Energy, ARPA-E. It's a collaboration with NIST and NOAA. And the basic idea is put a spectrometer out in the middle of the field, send laser beams from the spectrometer out over very long paths, up to 1 mile or more long. Little retroreflectors back there will send the light back to our spectrometer for detection. And then we measure the concentration of methane over these different paths as a function of time. This is a simulation of 2 methane leak plumes with real wind conditions out by the Boulder Atmospheric Observatory. And what you can see is as time goes by, these plumes are kind of changing direction and moving with the wind, and they intersect our different beam paths at different times. And so if we know the weather conditions, if we have good models for how the gas should transport, then we can take our measurements together with that knowledge and essentially back out where the leak was. It's inversion techniques that you see in a lot of different atmospheric science applications. So that's the basic idea. How can we make this low cost? I mean, I showed you a spectrometer that's kind of down in the sub $100,000 range, but still very expensive. Turns out that oil and gas operations are very dense. So if you go out east, there's about 40,000 wells east of us in Colorado right now. So within a 5-kilometer circle near Platteville, which is just east of I-25, all of these little yellow dots represent an oil and gas operation. Could be a processing or gathering facility, could be wellheads. It's unbelievable how much stuff is out there. And so if we have a range like 5 kilometers, we could cover hundreds and hundreds of assets with a single device, and then we could move that device from place to place to get even better cost savings. So actually, when you start to do the math on this, the economics of it look really good if you have a very nice centralized spectrometer. So that's sort of the deployment schematic and where we're going. So how are we doing in terms of progress? So we built that first fieldable frequency comb spectrometer. We brought the cost down into the realm of, possibility for doing something like this. And then we built this little mobile trailer. This is the frequency comb system sitting out there. This is this device. That's just a nice weatherized gimbal that has a transceiver on it, so it sends the laser beam and it also catches the return laser beam. And we can start to probe different path lengths, beam paths out in the open space with this. So we did that. We started out by testing how good the ARPA-E spectrometer was next to the proof of concept. And this was one of the neater things. So the proof of concept, you can see this is an Allen deviation. So what this is methane precision as a function of averaging time for our device. And it's in terms of ppb kilometers. So in the proof of concept spectrometer that I showed you earlier, we could get down to about 6 or so ppb in 5 minutes or so. With this is what we proposed to ARPA-E, and unbelievably, we got below our proposed precision line, which never ever happens, but we got lucky here. We got down to about a part per billion kilometer with this new device that's mobile. So just a really neat outcome on the spectrometer side. And as you can see, so as we start to average longer, the precision starts coming back up again, and that's almost for sure. We've got Picaros out there sampling at the same time, and we see the same uptick in the Picaro measurement. So it really comes down to just the variability of methane in the atmosphere at that point. So at the part per billion level, it is fluctuating at that level, even in windy conditions on a couple of minute time scale. Okay, so what I'm going to show you, so then we had this system, we got it fielded, we were starting to make measurements over long paths, and so we needed to start to make this into an automated system that could start to probe these different retroreflectors, and we wanted to see just how sensitive it was. There's a lot going on. I'm going to show you a video in a moment, so I'm going to explain it before it comes on, because everything starts moving at once. But so up here, this is our gimbal spotting camera. So we have these little retroreflectors about the size of my hand placed out in the field. We send our laser beam out there, and what you're seeing is this bright spot. That is the spot that's coming back from the retroreflector. So you're going to see it kind of wiggling around as the system, the gimbal system, tries to maintain alignment. Down here, this is the methane concentration in parts per million. And the red and the black points are these two different retroreflectors here. So we have a potential leak. Well, it's a leak we set, actually, at 500 meters. And then the black is an upstream beam, so a beam that's just upstream of that leak. And then the red is a beam that's just downstream of that leak. The wind is blowing this way. And so what you're going to see initially here, as I start this up, this is sped up 10 times, so that's why everything's kind of shaking around so fast, but you'll see it switching back and forth between the retroreflectors, adding points here that are just measuring the methane background. And then when we activate the leak, you're going to see the downstream beams start to pick up an enhancement. In this case, it's only maybe 15 to 20 or 30 parts per billion over where the background is. And you can see that background is fluctuating quite a lot. So as time goes by, I can probably speed it up here a little bit, you'll see more and more of those red points coming along. The black points, again, are upstream. So you can see the difference there is very clear, and we're picking up this leak. As I keep going along here, you'll see at some point we deactivate the leak, and everything kind of comes back, and the upwind and the downwind beam start to track each other very well again. And so what's neat about this is this leak rate was 8 scfh, standard cubic feet per hour, and that's about a quarter of the breathing rate of a human. So from about a half a kilometer, we can detect just this tiny, tiny methane leak. I think we were all very, very surprised that this actually worked. Again, that's the thing we proposed to do, thinking, well, shoot for the moon and hit the tree, but in this case, we actually were able to start detecting that very weak leak. So the next step, though, in this is we'd like to do more than just detect a tiny leak. We'd like to be able to tell the operators how big the leak is, because some leaks you want to fix, other leaks are so small that actually blowing down the system to fix it, you'll probably lose more methane than if you left it alone. So in order to do an inversion we need a very good forward model that can tell us how that gas is transporting in the wind conditions that we're making a measurement in. So these are some measurements where we have 4 beams now, 2 upstream of the leak, 2 downstream of the leak. A little difficult to tell here, but the green and the light purple are the downstream measurements. The black and the kind of magenta or whatever are upstream of the leak. So when we turn the leak on and we had the leak running for about 5 hours, this is again 8 scfh, you can definitely see the difference, the enhancement in those two, between the upwind and the downwind. So what we did is started to do different kinds of plume modeling to see how the forward model, how well could the forward model match our experiments. So we have a known wind speed and direction that we measure. We have a known leak rate. Can we get the plume model to match our observations? So the first thing that we did, we took these two, we're using this furthest upwind beam path as our background, and then we took the other upwind beam path, and of course they track each other. They don't see a leak. So that's as we would expect, and that's what the simulation shows. This is now switching to the beam that's just downstream of the leak. And so again, this is hard to see a little bit on this projector, but the observation is in red and the modeled is in purple, and you can kind of see these things are tracking each other quite well. And so we can do inversions off of this and actually get that leak rate to within about 20%. It's not bad because it's a small leak rate. If we move down to the next retro down, which is about 34 meters from the leak, you can see the enhancements are smaller. Both the simulation and the observation see the enhancement, just a few ppb at that point. And they track each other well, as you can kind of see as I zoom in here, but definitely not perfect. So in this case, this is a simple Gaussian plume model, which we don't expect to be that accurate. So we can't invert very well from that beam path. But we're working on high resolution, large eddy simulation modeling to try to get better plume models to back out the size of the leaks. And this is again using a different retro that's far away, and of course they track each other well. So that's kind of where we're at with the methane leak detection. I mean, the next step, we're starting to put up bigger arrays of different retroreflectors, put out multiple leaks, see if we can simultaneously differentiate them, and making nice progress there. So this has been a really exciting project. Okay, the last thing I kind of want to talk about is compact multispecies detection. And the reason I think this is important is because this open path system is nice, but it still takes a bit of a skilled operator to go out there and set everything up. There's a lot of equipment there. And I think one of the reasons why Picaro and Los Gatos Research and some of the other companies that are commercializing small, turnkey, push-button analyzers that can do real-time methane, water, et cetera, are successful is because you don't have to know what's happening inside of that box. You just push the button, it pulls the sample in, and it gives you a return. And so we're trying to figure out how can we achieve the sensitivity of that long open path DCS and take advantage of that bandwidth to measure multiple species, but do it in a compact deployable package. So this is funded by DARPA, you could probably guess, because I got to put a bunch of military applications on there and ships and people throwing UASs. But the idea is if we could create a self-contained sensing platform, you could send it out. And in this case, DARPA is interested in using this to sense like sarin gas, VX, all the bad stuff that they want to be able to detect using these frequency comb approaches in a cavity-enhanced modality. So the approach, as I just alluded to, is to couple the benefits of something called cavity-enhanced spectroscopy, which is what Picaro and Los Gatos research instruments are based off of, which is basically taking light and putting it in between two very, very highly reflective mirrors. So if you do this, the light bounces back and forth thousands of times. And then if you inject your sample in between those mirrors, it gives it a very long interaction path length. So it allows that light to a good long time to interact with your sample, and it boosts your signal. So we want to get cavity-enhanced spectroscopy together with the benefits of dual-comb spectroscopy that I went over earlier in this talk. Nice compact detection, broadband, high resolution. It turns out this is not at all easy to do. So actually, this is the first time I've talked publicly about this work. We've been working on it for about 18 months, and it's just getting to that point where we're starting to feel like, yeah, it's time to show people. as we get close. So I'm going to step through how we do this. There's your frequency comb, which again sends out this plethora of perfectly spaced wavelengths of light, comb modes. They're spaced at about 200 megahertz. And then we add an optical cavity. And so the trick, these are high reflectivity mirrors where we want to let the light bounce back and forth. If you're going to let light bounce back and forth thousands of times between two mirrors, you really need to set up the situation where you have an integer number of wavelengths between your two mirrors, because otherwise when it back reflects, you'll start to get destructive interference and the light just goes away. So we have to get wavelengths of light that have an exact integer number between the mirrors. So for a cavity, we also want the cavity to be small. So if we have a 7.5 centimeter cavity, basically this condition of having an integer number of wavelengths between the two mirrors occurs at about every 2 gigahertz of spacing. So that's where that occurs. The trick, and it's a serious trick, is you got to get your frequency comb modes lined up with each of those resonances. So I'm just going to push the button and move them over. In reality, that was like 9 months of the work right there. So was trying to figure out how to basically line up not just one wavelength, but line up tens of thousands of wavelengths with each of these resonances of the cavity. That was a heck of a trick. So if you do that, then the light that comes out of the back of the cavity is every 10th comb tooth. And then if we bring in our second frequency comb, just like dual comb spectroscopy, we can interfere every 10th tooth, have a unique beat note, and basically we're back to where we started from. We can use all of our nice dual comb spectroscopy tools that we've developed over time. So I'm trying to highlight the compactness of this. This is a view down. This is 7.5 centimeters. That's the cavity that contains these very highly reflective mirrors. There's some optics to kind of get the whole thing set up. And this is our entire detection system. It's just a $600 balanced photo detector from Thor Labs. Really compact, really cheap. And so it looks simple, but again, the trick is in controlling all of this. It's part of a slightly bigger system. There's the enhancement cavity and detection I just showed you. Here's what the frequency combs look like when we haven't packaged them into that nice little 19-inch rack mount. But I show this picture because what I'm hoping is that you can kind of dream the same way we're dreaming of all of this stuff with proper engineering could again be built into this tiny, tiny rack. So yes, it would be a little bigger than a Picaro, but not that big, not that much, I don't think. So we're excited at showing that in principle this should be able to work. So this is the first coherent dual comb spectroscopy through a cavity enhancement system. The way we knew this was working, this is the transmission of the laser light as a function of frequency. It's kind of noisy, but if you zoom in on this little piece here, you can see, what we could see is every 10th tooth was getting picked up in our dual comb spectrometer approach. So that's how we knew this thing was working, so we started to see every 10th tooth coming through. That was nice, but the finesse or the number of bounces between the mirrors was only about 7,000, giving us a path length of about 330 meters. Pretty good for a 7.5 centimeter cavity, but not as good as we'd like. Only 12 nanometers of bandwidth, and it took us 30 minutes to average this, and it wasn't good enough for spectroscopy yet. So this brought us up to a couple of months ago, and we were really scratching our heads and working on different ways to do this. The other problem was we were at 1550 nanometers, which is where almost nothing really absorbs. so this is absorption as a function of wavelength, and these are different species, water. This is transmission of water vapor. So you have to operate where water vapor is not going to absorb all of your light. But and there's CO2, methane, others in here, and you can see we're basically in no man's land. But that's where it was easiest for us to lock it up. But in the second generation now, we've just moved to about 1650 nanometers. That's where we start to get some of the nice methane absorption features. We redesigned the entire cavity to try to get better mode matching between the frequency combs and the cavity, and we achieved that. And so now what you're looking at is a spectra of a methane-enriched air inside of our cavity. So this is the cavity transmission. I cut out all the comb teeth and just connected the tops with a line. So what you're looking at here is the intensity of the comb spectrum, and then, these dips are all of the methane absorption features. So we were really excited to see this, but the postdoc Nazanin Hoghugi, the first day she got this to work, this is about a 1-minute average, we were really excited. she said, she called me up and she said, we've got a really good result, but you're probably going to want to see it before we show it to anybody else, because there's all of these crazy distortions of the absorption features. We should expect just kind of a nice, clean little dip and not some of these overshoots. And so we really thought, okay, this is strange. I mean, we can see it's working, but just not well. We went up and talked with some of the cavity-enhanced spectroscopy experts up at Gilla and Junyi's group. And they took one look at it and they said, that's a beautiful spectrum. And I said, what about these distortions? They said, no, that's nothing to worry about. That's just dispersion associated with the molecular resonances. So dispersion is very important to where those cavity modes line up. And so where we can get light to transmit through the cavity. And the presence of methane and the presence of methane absorption actually adds a little bit of dispersion right there where the methane absorbs. And so it shifts the apparent location of the cavity modes slightly across our spectrum. And so the end result is this kind of strange distortion of the line shape. So they helped us out with some interesting fitting codes that can take into account this molecular dispersion effect on our cavity. So you can see their data is in red as it was in the last look, and then the fit is in blue. So certainly not, and then I've switched this now from transmission to absorbance together with the fit. So the fit is not perfect, but this is not at all bad for a first cut. We were very happy with this. You can get a pretty nice return on how much methane is in there. That's 100 ppm of methane, which is nice, but in reality we only have about 2 ppm of methane in the atmosphere, so we tried it with that. You can see the dips due to methane get a lot smaller. Again, 1 minute average, but we can fit that just as well. Here's absorbance with some residual. And again, this is starting to be in the right spot where we can do some nice quantitative detection. So that's nice, but you can buy a Picaro that'll do this. and you don't need like a postdoc to work on it constantly to get it to work. So I'll skip over this slide. This is just showing, basically, we're doing a lot better. There's only been 2 other times that people have done a cavity-enhanced dual comb spectroscopy, and our bounces are much better, our bandwidth is much better, so we're doing really well in terms of performance statistics against the other 2 groups that are working on this. Okay, but anyway, so we're now moving on to 3rd generation. So we need to get beyond what the Picaro can do, because it's a nice instrument, and why wouldn't you just buy one if that's what you're after? So we moved even deeper into the infrared, so we've now shifted from about 1650 over to 1700. And what you can just barely see here is this gold curve and this light blue curve. Those are the absorption profiles of propane and ethane. And so now we're in a spot where we can get methane, propane, and ethane all lined up under our same little umbrella of transmission. And so we're starting to do this with mixtures. And then the goal is to move even further into other regions where we can start to get at many, many more hydrocarbons out by 3 microns. So anyway, you can kind of see this progression, hopefully, towards a sensor system that would look like a Picaro and act somewhere between a Picaro and a mass spectrometer. Okay, so let me summarize. So hopefully in the first part of the talk there, I convinced you that frequency combs and dual comb interferometry is kind of a neat technique that allows us to cover large spectral bandwidths at very high resolution. And the advantage of that is stability, precision, accuracy, things like that you would really like in a sensor. In the methane leak detection section, we were talking about our first field deployed spectrometer and that we are starting to pick up these very sensitive methane leaks from a long distance. And then finally, hopefully that little section whet your appetite a little bit towards what we can hopefully do in the future in terms of getting real-time instruments that could fly on an airplane to you guys to start doing really good science. So I think that's it. Oh, I want to, of course, the support. So NIST and the NRC for my work, their early work on the proof of concept, and then DARPA and ARPA-E and NSF as well. Okay, thank you.
Thanks, Greg. Are there any questions? I have quite a few, but...
Okay. Yeah.
I was just wondering about, like, are you using, my understanding is that you're using hydrogen for that?
Yeah.
It's just a what? Do you think it's good enough or
Yeah.
kind of process?
So yeah, no, I think that's a great question. So we're actually using Hytran 2008 for methane because Hytran 2012 we see a 5% change in the methane concentration, and it moved us further away from the Picaro that's been calibrated. So the answer is, I mean, Hytran at atmospheric conditions is getting really good. It gets better and better and better. But like methane, for whatever reason, was not as good this time around. And so we've been talking with the Hytran guys just to let them know that's what we saw in case other people are seeing that. So at the end of the day, yes, they're good, but they're not quite perfect yet. And so we've been doing some work like this in combustion. And when you go to high temperatures, Hytran does not do nearly as well. So, yeah.
What's the largest distance that you've attempted?
So we've done about a mile. Our colleagues at NIST have actually sent it all the way across Boulder now. So that was 5 kilometers each way, 10 kilometers round trip. It really comes down to how well you do it. You know, it comes down to the optics at that point. So to get that long path length, we'll go with a bigger telescope, you know, to keep the divergence down and also give you a bigger collection aperture. So I think one could go farther than 5 kilometers, but you get bigger and more expensive equipment as you get out past that. Yeah.
So what sort of large eddy simulation technique are you using?
Yeah.
Plume, and who's doing it?
Yeah. So what I showed you there, the forward models, was just simple Gaussian plume. The large eddy simulations are being done by Kuldeep Prasad at NIST in Gaithersburg, and it's based on FDS. It's the fire dynamics simulator. It's actually an LES code that's been adapted out for atmospheric work. It was originally built to do fluid dynamics inside of buildings. But this is an area that we're pretty actively, still interested in what other people are doing. I mean, this is an area where we think there's room for kind of changes in what we're doing. We haven't gotten something yet that we just say, this is perfect, it works, we don't need anything else. So we're certainly open to collaborations there, yeah.
So can you beat the signals in from one of your lasers against either reflected or direct solar radiation?
It's tough because the answer is yes, we've tried to kind of do it almost like an FTIR where some people have a solar FTIR where they have sunlight coming in and then they operate a Michelson interferometer to get a signal. The problem is that our comb teeth are very, very narrow. There's a lot of, we can get a signal, but it's weak. It's not very usable because we need to bring in that light, beat it against the comb, and a lot of that light is not, I don't know what the simple way to describe it is, but it doesn't work well with incoherent radiation, basically. Yeah. Yeah.
That was a fun talk.
Okay.
I had a quick question about the projecting out. How do you think you'll compare with like FTIR spectrometers in terms of like sensitivities and things?
Yeah.
Some of the higher molecular weight hydrocarbons.
Yeah. So I think the benefits of the dual comb to an FTIR, there's no moving parts in a dual comb, so it can be made much smaller. The resolution of this dual comb that we have, it's about a 19-inch rack mount, is comparable to a FTIR with a several meter Michelson arm. So these are big devices that are hard to move. We're sort of in that range of where the TCON network is, if you're aware of that network of big FTIRs that look up. But so that's the benefit. The downside is that we can't cover the same wavelength range. So with a frequency comb, getting hundreds of nanometers is not so difficult. To get, several microns from 2 to 4 or 5 is very hard to do right now. That said, under the DARPA program that's funding this cavity enhanced work, there are about 8 or 9 other teams that are working on mostly frequency comb sources to try to get better mid-infrared, far infrared, terahertz sources even. So I think over time it will get there, but boy, it's hard to beat. I mean, those FTIRs cover such a monstrous range. So then coming back, I guess, to finish the question, the resolution is useful in the sense that even if you're looking for a broad absorber, you have interference from sharp water vapor and methane lines. And so being able to resolve with no instrument line shape the difference between the water, the methane, and the underlying broad absorbers, I think is going to be a strong benefit of this technique once we get out that way. So not there yet, but the Bruekers of the world still have a definite place in the new world with frequency combs, yeah. So, yeah.
Pressure is your cavity at your cavity.
So we've just been doing atmospheric pressure. Yeah, lowering the pressure is a possibility for kind of improving spectral congestion, although we haven't gotten to that point yet where we're worried about it. So right now we're just filling the cavity with room air or with a premixed sample. Yeah.
So for that cavity where it's 7.5 centimeters, is that adjustable and for changes like temperature? I can see that it can be very, very precise.
Yeah. So we on one end of the cavity we have a piezo stack that one of the mirrors sits on a piezo stack, and so we're actively controlling all of the time the length of the cavity. And then in the picture we actually have a name for this for the cell mount here. This thing, that's a very large piece of stainless steel. And so we call it beefcake because it weighs 40 pounds or something. Anyway, and you can make some of the people over at NOAA and I like Instar, many places there are better cavity designs that use carbon fiber and other components that reduce some of the thermal drift of the cavity. But right now we just actively control the cavity and use a pretty beefy cavity. So. So yeah, in the open path, we were able to get 13 CO2 and HDO. We can't quite see 13 CH4 at our signal to noise levels yet. Some people have asked about 14 CO2, which would be great, but that one is really hard to get. We can't see it yet. So it comes down to the strength of the absorption and how much is there. But absolutely, yeah, we can already see some of the isotopes. Excellent. Thanks.
Thank Greg again for
Thank you. Yeah.